Hi, M10 online students. So in this week's discussion about Test 1, a couple of people said they'd like more information about the empirical rule and z-scores and using the 1.5 IQR method to detect outliers. And also some people said they just wanted more videos. So I thought I would make a video about these topics in case you'd find it helpful. So this first example is using the 1.5 IQR method to detect potential outliers. And again, this method is used whenever we have a skewed distribution. So a sample of roller coaster heights had a right skewed distribution, and I give you the values for Q1 and Q3. The question, should the highest coaster be considered a potential outlier, meaning unusually tall, compared to all the rest of the coasters in the sample? So what helps me is always making a picture. So your data is laid out. Here's Q1, here's Q3. And the idea behind detecting a potential outlier is you need to find the location of this value here, which is called the upper fence. There's also a lower fence, which would be down here, but we're not asking if any of the coasters are unusually short, just tall. So we'll find only the upper fence. And the upper fence is located 1.5 IQRs from Q3. Similarly, the lower fence is located 1.5 IQRs from Q1. And so to find the location of the upper fence, we would take Q3 and add on 1.5 IQRs. Now notice that the IQR wasn't given in the problem, but we were given Q3 and Q1. So just as a reminder, the IQR is simply Q3 minus Q1, or in other words, 33.2 minus 8.5. So let's take a moment to compute that. If we take 33.2 and subtract 8.5, we get a value of 24.7. So to find the upper fence, we're going to take Q3, which is 33.2, and we're going to add on 1.5 times the IQR, which is 24.7. So let's take a moment and compute that. That's going to give us a value of 70.25. So the upper fence is located at 70.25 feet. And so anything out here above that is considered a potential outlier. In other words, unusually high. And so 128 is definitely beyond 70.25, and so we would consider it a potential outlier. And that's the 1.5 IQR method. Something someone else asked about, or several other people said they struggled with, was the standard deviation and z-scores. So this is just a slide that summarizes those two statistics. So the standard deviation measures the average distance from the mean of all your data values. And there's a formula to compute it, but in practice, we use technology. So we would never compute standard deviations by hand. Z-scores measure how many standard deviations from the mean a particular data value is. And we're going to use a z-score to do two things. One, to determine if a data value is a potential outlier in symmetric distributions, and we'll talk about why that's true. And secondly, to compare data values from different distributions. Now, the z-score formula is probably one of the only formulas that you should have on your note sheet for the test. So z is equal to the number that you have minus the mean divided by the standard deviation. This is not something that's done automatically in any technology. You have to actually subtract and divide using a calculator. Okay? So let's do an example of each one of those. Using a z-score to detect potential outliers in symmetric distributions. So 3-year-old boys have a mean height of 38 inches and a standard deviation of 2 inches. Is a 3-year-old boy who is 43 inches tall, unusually tall compared to his peers? Why or why not? And the distribution of heights is symmetric, right? So we would have to know that the distribution, or be told that the distribution of heights is symmetric. Now, in order to explain why the z-score can help us do this, I'm just going to revisit something called the empirical rule. So I'm going to draw a unimodal symmetric distribution. I'm just going to smooth it out. And so this is a picture of a unimodal distribution, always centered at the mean. And we have something called the empirical rule that says that if we were to go out 2 standard deviations to the right, so each of these orange hops represents a standard deviation, and 2 standard deviations to the left, we would enclose 95% of the distribution. So any value out here in this little tail would be unusually high, and any value out here in this other tail would be considered unusually low. And why is that? Well, the whole thing has to add up to 100%. So if we know that 95% is in the middle, that means 5% is in the tails. That means 2.5% is out here, and 2.5% is down here. So if you're in the top 2.5% of a distribution, we say you're unusually high. And if you're in the bottom 2.5% of a distribution, we say that you're unusually low. It's just kind of an arbitrary cutoff, but I do think that most of us would agree that being in the top 2.5% of anything is kind of special. All right, so let's figure out if this child who's 43 inches tall is unusually tall compared to his peers. So we're going to use a z-score to do this because the distribution is symmetric. So z is equal to our number, 43, minus the mean, which is 38, divided by the standard deviation, which is 2. And we'll take a moment to compute this. So 43 minus 38 divided by 2 gives us a value of 2.5. So this youngster, this young boy, is 2.5 standard deviations above the mean. So this is 1 standard deviation, 2 standard deviations. His height would be up here. He's definitely in the top 2.5% of the distributions. So we would say yes. Why? Because he's beyond 2 standard deviations from the mean. He's in the tallest 2.5% of children of his age group. And finally, the second thing a z-score can be used to do is to compare 2 distributions, values in 2 different distributions. So the SAT and the ACT are common assessments taken by high school seniors who are interested in applying to college. And they have very different scoring systems. So for the SAT, the quantitative SAT, the mean is equal to 500, and the standard deviation is equal to 100. For the ACT, the scoring system is much lower. The mean is equal to 21, and the standard deviation is equal to 5. And so both distributions are symmetric. Which is more unusual, a quantitative SAT score of 750. So suppose a young person gets 750 on the quantitative SAT. Let's find their z-score. Well, their z-score would be 750 minus 500 divided by 100. And if we take a moment to calculate that, that's going to be 2.50. So that's definitely an unusually high SAT quantitative score. Now let's compare that with the ACT. The ACT score of 28. That z-score would be 28 minus the mean divided by the standard deviation. And let's take a moment to do that. That would give us a z-score of, let's try that again. That one gives us a z-score of 1.4. So on the SAT, the score was well over 2 standard deviations above the mean. And on the ACT, it was above the mean, but not by as much. If I were to graph those two z-scores, okay, so remember the mean is in the middle, and you go out 2 standard deviations. Okay, so the first one is here, over 2 standard deviations above your mean. And the ACT one is, say, here, a little over 1 standard deviation above the mean. And so definitely the performance was better on the SAT. So I hope that helps, and as always, just feel free to send some more questions, but I thought I would make that short video based on some of the comments I saw in the discussion.